All right, this is the Friday tutorial. We're free to talk about anything we want, particularly because next week is test week. What we're gonna do is we're gonna work through the students who are in the room have suggested that we look at test 3 problems that could be on the test next week. This is the June 24th test of last year, the summer physics test. These are the problems we're going to work on. Just as a reminder about this particular test, this is a summer test. The first time I ever taught summer, you're in class for 2 hours a day, so what I did is I gave them an hour-long test, and then I gave an hour-long lecture immediately following the test. And the first and only time I did this, they stared at me for the second whole hour, hating me. So I decided to change it up. What I did was, I'd write hour 15-minute tests with the full intention of, I'm gonna give them the full 2 hours. So I wasn't that worried about giving big tests. If this appears to be too big, it's because you guys are used to 75-minute tests, and this test was written with 120 minutes in mind. So problem 1, given a simple pendulum that oscillates 5 times in 4 seconds, or 4 pi seconds. So 5 t equals 4 pi. Well, that's a very odd time. Do I have to multiply it out? No. Dr. Eschenberg is trying to get the problem to work out nicely. He has done a service for you. It's a simple pendulum. Period equals 2 pi L over G. We're looking for length, so we have to extract length out of this. Period squared, 4 pi squared, L over G. Period squared G over 4 pi squared L. And that's the length. Well, what's the period? The period is the total time divided by the number of oscillations. Or period squared is time squared over n squared. So this becomes t squared G over 4 pi squared n squared is equal to L. The t is 4 pi quantity squared G over 4 pi squared n squared. This is appetizer. On test 3, how I would probably look at the versions, I think the version is the length of the rope, or probably the number of oscillations. This gives you 16 pi squared over 4 pi squared G over n squared. Those cancel, that gives you 4. So you're left with 4 times 10 over 5 squared. So 40 divided by 25. Yes?
So finding L, I bring G to the top. G and T always stay next to each other when you're bringing G to the top.
G and T always going next to each other. In this particular case, it did. But in terms of, you need to know this, and then if you also know that that's true. So it could, yes. All right, problem 1. The helium-filled sphere is held to the ground with a string. Given the values listed, what is the mass of the balloon? So we're looking for the mass of the balloon shell. The volume is 800 cubic meters. It's helium inside, so all of the values are given. The force diagram, we have the buoyant force, we have the tension in the string, we have the mass of helium times gravity, and then we have the mass of the balloon times gravity. So those are the four forces. What do we know about the balloon? It's doing nothing. It is sitting there. So it is neutrally buoyant, so the sum of the forces is equal to 0, which means FB minus MHEG minus T minus MBG. We're looking for the mass of the balloon. MBG. Buoyant force, density of air, that's the fluid being displaced, volume times gravity, minus mass of the helium. We don't know, but what we do know is that density is mass over volume, so mass is density times volume. So this becomes density of helium, volume, gravity, minus tension. Divide everything by G. The mass of the balloon is density of air, volume, minus density of helium, volume, minus T over G. And then you just plug and chug everything. You've got density of air, helium, and volume. You've got tension, gravity is 10, done. So that's problem 1. Now problem 2, something like this will be on the test. It is called an Atwood string. Technically it's not an Atwood's machine, but this is as close as I can get to an Atwood's machine and still maintain the statement. Physics 213 will always have an Atwood's machine on the test or final until they get it right, which means it will always now be on the test. I give you the frequency of the string plucked. Now obviously, which part of the string do I pluck? L1 or L2? This is one of those dumb questions. L1. If you pluck L2, it just flops back and forth and it's not going to make any sound. So it's got to be L1. Frequency of a string is NV over 2, whatever's vibrating. So N over 2, in this case, we're going to have L1, and then tension over the linear mass density of the string. Now, because this mass is hanging off the end, it's providing the tension to the string. If we're just going to do a simple force diagram, T up, MHG down, so T is equal to MHG. And this becomes N over 2L1. T is MHG. Now it comes to lambda. Lambda is the linear mass density, the mass of the string divided by the length of the string. I wanted to know the mass of the entire string. It's explicitly stated. So the total length of the string is L1 plus L2. So this becomes mass of the string L1 plus L2.
You're flipping that because lambda's in the bottom?
Yes. Lambda is in the denominator, and this is sometimes I do, when I, hold on, dial it back, fans. When you see this, that's me preparing to do a substitution. Lambda is in the denominator, so I can think of this as 1 over lambda, and then I just substitute it directly in. I use it as a way to minimize the possibility that I'm gonna wreck this up. So I know, normally what I do is when I do a substitution of an object in the denominator, I flip it before I insert it. So this is it. Question, or actually, the task, solve for m sub s. So this is f squared n squared over 4l1 squared mhg l1 plus l2 over ms. Solve for ms. ms n squared mhg L1 plus L2 over 4L1 squared F squared. And so all you do now is just plug it in. The alphabet soup mode is the way to go.
Why is lambda mass of string over 4.2?
Because I did not give you the total length of the string, but I did give you the length of the two parts of the string. So the total length of the string is L1 plus L2. The length of the vibrating part is just L1. I need to put that in focus. Done what? NV over 2L. It's the square root of 2 over 1. That's substitute. Oh, okay, I'll include that on the piece.
That's one of those bigger clouds.
Yeah. I mean, pretty much the appetizer uses this, and this. Problem 1 uses this. No, not that. Uses this, that, buoyant force. I think I may, if it's not here, then I probably wrote it up on the board at the time. Sum of the forces is equal to 0. I don't think that's necessary. You should know that. Ah, thank you. All right, the last thing. Doppler shifting, Pied Piper. This is a roulette wheel problem. You hear 350 hertz coming at you, but going away you hear 150. So the first thing you want to do is you want to figure out that velocity. I think we've talked about it before, but the primes are a little bit redundant. Towards for a moving source, F over 1 minus V over Vs. Away, F over 1 plus V over Vs. Those cancel, and Ft over Fa is equal to 1 plus V over Vs, 1 minus V over Vs. Now we just solve for V, cross multiply. Ft, 1 minus V over Vs, Fa, 1 plus V over Vs. Distribute. Ft, Ft, Fa, Fa is this.
Why'd you flip the sign back over?
What happens is that this is in the denominator of the denominator, so it goes in the numerator. This is in the denominator of the numerator, so it's in the denominator. Get all my V terms on one side. Factor out V and Vs. And so that's the velocity. That's the velocity of the motorcycle. Excuse me. Now we need to find the length of Pied Piper's pipe. It is opened at both ends and is at its fundamental frequency. Now really what we need to figure out is what is the fundamental frequency of this pipe. And to do that, we would use either towards or away, it doesn't matter. So the frequency of the pipe is the frequency towards 1 minus V over Vs. And that will give you the frequency of the pipe. The last part, what is the length of the pipe if it's open at both ends and at its fundamental frequency? The F is NV over 2L, so L is NV over 2F. And so that's the length. So in terms of the length of this test, I think it's appropriate. I think it's a good test for you guys. It's a little on the short side for a 2 hour. It's way short normally for a 2 hour. Yes? Oh, N is the harmonic. So since we're at the fundamental frequency, N is what? 1, correct. Mm-hmm.
So what is it, V, that's the last part of the equation, and velocity? Is that right?
Well, this velocity here, actually, let me be specific. That's the velocity of sound in air. That particular V is 350. Not this V here. This is the velocity of the bike. That's the velocity of sound in air.
So in that equation, V is always sound there.
V what? V sub S, yes. The V that's used in this is 350. This VS is 350.
That 2L is only 4L.
If it's closed at one end, yeah. Good.
And you flip, like you said earlier, you flip it with the numerator and the denominator. And
Yeah, this is, simplifying it, this is 1 over A. Let's look at this. 1 over A divided by 1 over B. So this is in the denominator of the denominator, and this would end up becoming B over A. You could have an intermediate part where it's that becomes A inverted, that becomes B inverted, and A inverted is 1 over A, and 1 over B inverted is equal to B. So you get that. And so that's the test.
so far I'm seeing two people
What?
doing all that, all the math right there where it says F.
Yeah, the roulette wheel stuff you gotta do. Yeah.
Just multiple choice.
Yeah, let's crank through that. I wanna do the one that I have. I mean, there are other versions. It's the same stuff, effectively. All right. Oh. What, Oh, this is funny. I have the Taylor version. On page 5, there's a word at the bottom. It's probably Taylor, Oxford, or Abbeville. You got Abbeville. Everybody have Abbeville? Okay, I'll do that Abbeville one. So the problems were from Taylor. This will be the multiple choice from Abbeville. Now, on the test, what had happened was people shot out, people started reading the test and going, what's this whole deal with the strings? Because I go string 1, string 2 through string 5. What I did is on the front of the classroom, on the chalkboard, I had written those 5 symbols. One where it's the ends are fixed and it's vibrating in the pattern as written. So now we've got that. Let's dig through the problems. Units of pressure are what? Pascals. A spring pendulum has a period of 2 seconds. You quadruple the mass. Its new period is what? The period is 2 pi m over k. If you quadruple that, a 2 pops out, so it has to be 4. What is the equation for Pascal's principle? PA is equal to PB. Regardless of the depth, the pressures are equal if they're at the same depth. You measure the period of a pendulum, it's 3 seconds. You increase the mass at the end of the pendulum, its new period can be simple pendulums are mass independent, so it's still 3 seconds. What is the equation for the frequency of sound heard by a source, moving source towards observer? So moving sources means that it's either A or D. Since it's moving towards, the frequency has to be higher. Therefore, the denominator must be less than 1. So it's D.
I thought the moving source is F times.
It's the moving observer where the parentheses are in the numerator. The
Okay,
parentheses are in the denominator for a moving source.
Okay, so if you're trying to find the frequency of the source, you have F over 1 plus or minus.
Yeah, if the source is moving, then you use that, correct.
Where did I do wrong?
You were picking the moving observer. The velocity of sound in a vibrating string, in this realm, there are 2 answers. It's either A or E. I'll proof it over the weekend, make sure that stuff's out. You measure the spring constant of a spring on the moon. It's 300 newtons per meter. You bring this spring to the earth. Its spring constant is now what? It's the same. What's the first word of spring, or second word of spring constant? Constant. It doesn't matter if it's on the moon, earth, out in space. It's the same. A simple pendulum is, and you could probably tell that it's got to be that one or that one, independent or dependent on mass. It's independent of mass. You bob up and down 20 cycles in 10 seconds in a wave pool. Your period is what? Period is T over N, so it is 1/2 of a second. 10 divided by 20. 2 strings are identical length, material, and tension. They both resonate at the first frequency. One string is thick, the other is thin. The thicker string has the lower frequency. Thicker string means higher mass density if it's of the same material. Higher mass density, lower frequency. Object is negatively buoyant. Which of the following is true? It's got to be A. If it's negatively buoyant, the forces add up to be less than 0. Which string has 2 antinodes? Two. And in this case, it's the same thing for 13. I'm just guessing how I wrote these. The antinodes are the parts that move the most. Yeah. So there's 1, 2, 3, 4, 5 antinodes. 2, 3, 4, 5, 6 nodes. So as written, what's that? The N for a third overtone for a string is what? Is what? N equals 1 fundamental frequency. N equals 2 first overtone. N equals 3 second overtone. N equals 4 third overtone.
What is when you cannot have any even number frequency?
How many nodes exist on a string that's at its third harmonic? So this is its third harmonic. How many nodes are on that string? There are 4. Lambda is what?
Maximum string divided by the length.
Yes. For a resonating half pipe, i.e. a pipe closed at one end, the third harmonic is the same as, and actually, oh yeah, it's correct.
The first overtone.
It is the first overtone. Because it's an odd harmonic, it does exist. So the ends are 1, 3, 5, etc. 1 is the fundamental frequency. 3 is the third harmonic or first overtone. Wood floats in water. It is not completely submerged. Density of wood is what? Now, it's got to be E, less than water.
What would be the N for something? 3?
The N for 17, it would be 3. Because the N's just go 1, 3, 5, 7, 9, etc. When you decrease linear mass density of a string while keeping tension constant, the velocity of the waves in the string, it increases. Because what is velocity? Square root of tension over linear mass density. You bob up and down 20 cycles in 10 seconds in a wave pool. Your frequency is what? Its frequency is N over T, so it's got to be 2 hertz. Hooke's law in vector form is what? A. At the node of a vibrating string, which of the following is true? D, it doesn't move up or down. When N equals 2 for a resonating half pipe, the frequency is called what? It can't resonate, so it has to be C. No, what it's doing is really, it's just doing that. It's not moving up or down like any node would just move up and down. At a node, it will just move like that. But its vertical position doesn't change. The object is neutrally buoyant. Which of the following is true? Sum of the forces is 0. Here is a moving source away from an observer. So to get away, you have to have a lower number. Denominator must be greater than 1, so it's A. It's moving away from a stationary observer. So it says source. Heard by a source, moving away. So it's moving away. All right. What's next? Problem set 10. Okay, we did number 4 in class on Thursday. Which one do you want to work on?
5.
5? Okay. A pulley is 1.8 meters away from the wall. A 4-meter string that has a mass of 25 grams iron mass is hung from the end of the string hanging off the pulley. When plucked, it produces a fundamental frequency of 2000 hertz. What is the mass of the iron? Okay. So the frequency is NV over 2L. V is the square root of tension over linear mass density, which means N over 2, I'm going to call this L1, that's the length of the vibrating part. V is tension over lambda. Now tension is provided by the hanging mass. So frequency is N over 2L1 mHg over lambda. Lambda is the mass of the string times the total length, which I will call L sub t. So F is N over 2L1 mHg LT MS. It's the hanging object, yes.
It's LT, just L1 plus LT.
Yes. Well, really, LT was given to you straight up at the beginning. Because in the second sentence, it says a 4-meter string.
Yeah.
I was just being thorough and I just wrote
Okay,
2.2.
Yeah.
I think 2.2 is unnecessary for the problem. Yeah. Well, really, 1 over lambda is LT divided by MS. So that becomes this. Now the goal is to just find the hanging mass. F squared, N squared, 4L1 squared, mass hanging G LT over MS. So MH is equal to that. Yep. And so that'll give you the hanging mass. I kind of am, but
Multiplying by us.
yeah. I'm multiplying both sides by this denominator, and I'm dividing both sides by that, that, and that. Okay. Take this mass and experiment to the moon and find its first overtone and third harmonic. So first overtone, N is equal to 2, and for third harmonic, N is equal to 3. The frequencies are N over 2 L1. Oh, goodness. MHG. I'm going to use this equation right here. I know MH, I know MS, I know G, I know LT, I know L1. Plug in 2, recompute. Plug in 3, recompute. You've got those two frequencies.
Back to the other question
Yeah.
there. Is this still the same question, or is
It's the same system. The first part of the system, we're on Earth, and we need to figure out the mass that's hanging. Then we go to the moon. Oh, there is one catch. The G in this equation, because we're on the moon, is 10⁶ meters per second squared.
I was trying to figure out why it's mass, strain, tension.
Yeah, it's the same problem, except that now frequency is an unknown. Hanging mass is a constant, or is a known quantity. And you were asked to just find frequency. All right, next problem. What?
Would there be any buoyancy with water and
Could be.
more depth on that? Any one on there?
Underwater?
Yes, I think it was the one that's on the online lecture.
Uh,
You asked about the ratio for it. I mean, certain like that.
okay. You have a sphere underwater. The volume is 100 cubic meters. Oh, I'm gonna have to get the numbers right. There's a tension given in the string, and it is 4,000 newtons, holding it down. The mass of the infinitely thin shell is, oh, I'm gonna have to figure this out. What I would do, I mean, this is one of the reasons why I do alphabet soup mode. But given the mass of the shell, given the tension of the string, given the volume of the object, V1 is the volume of vacuum within that object. V2 is the volume of rebellium liquid in the sphere. The density of rebellium is 2,000 kilograms per cubic meter. Now, really, I don't know if these numbers work. What may end up happening is if it is numerically impossible, I'll just change the numbers until I get something that works. But really, what I want, the question that would be asked of me as an undergrad, because they didn't give a dang about numbers either, is give the ratio of the volume of rebellium of the total volume. So what fraction of this sphere is rebellium, and give it as a function of ms, t, density of water, density of rebellium, probably gravity's in there too. Give me that function. And then what happens is, then you just throw in the numbers and then you're happy.
That could be the space that's in the balloon that's not rebellion, right?
Well, yeah, there are different ways to express this, but in this particular case, I'm looking for the fraction of volume that's rebellium in the sphere. We're going to explore this problem. The forces on the sphere are buoyant force, mass of the sphere times gravity, tension, and then the mass of rebellium times gravity. So there are three forces acting on it. V1 is vacuum. It has no mass. Or you could say it's a gas and its density is so light that it doesn't really matter. It's it's in a neutral equilibrium state. So FB minus T minus MSG minus MRG is equal to 0. I think I'm going to need the jackknife equation. Density is mass over volume, so mass is density times volume. A Swiss Army knife, jackknife, I don't know. The katana of equations. So 0 equals buoyant force. Buoyant force is density of water, volume displaced, or V, times G. Tension, the mass of the shell is given, so that's there. And then I have mass of rebellium, which I don't have, but that's rho rebellium V2 G. And let's see, I may be able to solve for, since I know total volume, let's identify what I know. I know water, volume, gravity, tension, mass of the shell, gravity. I know the density of rebellium and gravity. I can solve for V straight up and get a number. So this becomes rho R VG equals rho W VG minus T minus MSG. Divide both sides by G. divide both sides by rho r. And that's the volume. Now, to get the fraction, woo, thank you. I should be labeling this stuff correctly because this goes over here and I drop the subscript. So that's 2. That remains the total volume. That's 2. That's 2. And what number do we get? 1 over 2,000.
We forgot.
Oh, it goes right here, does it not? There it goes. So it's 1,000 divided by 2,000. V is 100. 4,000 divided by 10. Oh, that's going to be bad. Density of water is 1,000.
No, but
Isn't that multiplied like just that first volume term?
yeah, it should be 1 over density divided density of water.
Hold on. Blah, 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 blah. Thinking. Oh, crud. All right, hold on. I see what you're getting. What I did initially, I went from here to here, divided everything by G. That goes away, that goes away, that gets dropped down, that goes away. Now I'm dividing everything by rho r. So V2 is 1 over rho r. Then I keep that. Rho WV minus T over G minus MS. Yeah, dividing all of it. So this is 1 over 2,000. 1,000 times 100 minus 4,000 divided by 10 minus mass of the shell is 100. And the volume is 49.75 cubic meters. Which means that V2 over total V is 49.75 divided by 100, or 0.4975.
That will always be meaningless
Because it's a fraction. I mean, what do you get when you take cubic meters and divide by cubic meters? You get nothing. So it's unitless. Huh? V is the total volume. What I solved for here was the volume 2, or the volume of Rebellion. To get the fraction of the volume filled up by Rebellion, you take the volume of Rebellion and divide it by the total volume. To get the volume of vacuum, you could do this. Or get that.
Do 8 problem set
8, problem set 10. Okay. a 0.65 kilogram cord is tied between two strings. Oh, this is another important thing. This may be the reason why I don't grade number 8. Because I don't give you the distance between the two trees. Let's just say 10 meters. The tension in the cord is 200, oh wait, it may be a pleasant surprise. 240 newtons. Let's temporarily get rid of that. I may have displayed a moment of brilliance. So what is velocity? It's the distance divided by the time. Or the time equals the distance divided by the velocity. Well, the velocity of a wave in a string is NV over 2L. L is the length of the string, so N over 2L tension over linear mass density. Keep writing rho L, but we should use lambda. So 1 over V is 2L over N Oh wait, no, I don't need this. Hold on. V is, oh God. It's Friday afternoon and I'm crazy. V is just T over lambda. There we go. So 1 over V is lambda over period. Oh, thank you. So the distance is 2L. 1 over velocity is lambda over period. And that's the total time. We will need length. Bringing the L inside I get that. Now lambda is mass per unit length, or mass of the string divided by length. So this becomes 2L squared ms over LT. One of the L's cancels.
How can you say T? Okay.
T is given.
Distance is
T is a given, yeah.
Are you crossing out 1 over the 2L and are you crossing out?
Well, I crossed all this out because I don't need to know the frequency. It's all about the velocity of the wave in the string. So that's the time. Now, one of the things that we could do is, I'll sit here and go, maybe we should double check the units just to be safe. It's the square root of L meters, ms kilograms. Tension is units of force, which is kilograms meters per second squared. The units check.
You're gonna have to put D in there because distance is equal to length.
The reason why the distance is 2L is because the question says, how long does it take for the wave to travel from one Oh wait, one tree to the other. I didn't say there and back, so that goes away. And big deal. So we divide by 2. It's not complicated. It's just, it's Friday afternoon. I'm coming down with some type of bug, and I'm mentally out there. Just, I'm going down.
Can you show those? What did you say? Put in for L.
Oh.
In this problem, we would have to be given the
Excuse me?
link. In this problem, we would need to be given the link.
Yeah, I'd have to give you the length, which pretty much effectively violates this as a, like, I'm not going to grade this problem. But for your benefit, if you want to set L is equal to 8 meters, then by all means, just set it that. Oh, goodness. I'm dying.
There you go. Friday.
It is Friday.
Use 9 as well.
9. Okay. Number 9, we gotta read it. A train whistle is a pipe that's only open at one end, emitting a sound at its second overtone. So second overtone for a pipe at one end is 5. The train is moving at 75 meters per second towards a train station. You are standing at the train station and hear the whistle at a frequency of 4,000 hertz. What is the length of the whistle? So it's a hybrid problem. It's a Doppler shift on top of a pipe problem. So the resonant frequencies of a half pipe are NV over 4L.
And that V is just 75, right?
No, this particular V is the velocity of sound in air. This is the frequency that's created. The frequency that you hear, since it's a moving source, is F, that F, divided by 1 minus V over Vs. So in this case, because we're using the velocity of the train and the velocity of sound, we're gonna have to be very specific about what our Vs are. For pipes, it's the velocity of sound in air.
So you just have to substitute NVS over 4L.
Yeah. So Ft is equal to NVS over 4L 1 over 1 minus V over Vs.
This on a different.
No, this is the same problem. We're still on 9. We're doing problem set 10. So all I'm looking for is L. So L is equal to NVS over 4FT 1 minus V over Vs. And that's it. That's all you got to do. Say it again.
Velocity of sound in air is 350.
350, always 350.
When you sub the ST and the 1 over 1 minus VS in for frequency, why wouldn't it be FT times 1 minus V over
Because it's a moving source. You're an observer. This is a moving source towards you. If you were in the train and the train station was emitting a frequency,
So like, you started with the moving source equation, so when you're isolating that F, why would you multiply that times that? Basically asking, when you put it over here, why isn't it 1 minus V over Vs?
what I did here is I did a full substitution of F, and F is this. And then I just isolate L.
So we would have to multiply that by 100, right? Because it says centimeters. We just multiply the.
Yes. Yeah. Once you get done with that, that answer's in meters. So you multiply by 100. All right. Anything else? Are we? It's the same old stuff. 1, 2, and 3 aren't bad. We've done 4, 5, and 9.
What did you say, Mr. Messenger?
We've on problem set 10. We've done 4, 5, and 9. 1, 2, and 3 is trivial. 6, 7. Oh, we did 8. 6 and 7 are not that bad. It's just applications of frequencies. And so I think we're effectively done. All right, going once, going twice.
That's Friday.
It's Friday. Go home.